When a high-speed robotic actuator is commanded to stop, standard proportional integral control typically causes the system to either overshoot its target or require time to settle. Achieving a sub-microsecond settling time, where the system snaps perfectly still without vibrating, is often considered a violation of physical control limits. By bypassing traditional digital sampling delays with predictive state observers, engineers can remove the phase lag barrier that restricts standard feedback loops. This architectural approach enables nanometer-scale precision in high-speed motion, reaching performance levels that traditional control models cannot support. High-speed motion control depends on an architecture where the system's software update cycles are physically locked to the hardware's pulse modulation frequency. A baseline standard closed-loop vector control system operates by measuring errors and applying corrective forces. No matter how well-tuned this reactive loop is, it inevitably hits a physical performance ceiling. This ceiling is dictated by the absolute lower bound on sample rates. A system's sample rate must be at least twice the bandwidth of its reference inputs, and to effectively suppress random physical noise, the sample period should be 10 times shorter than the noise correlation time. This diagram illustrates the failure state of discrete time systems at high speeds. The continuous time signal curve is broken into discrete sampling points, creating dead time blind spots between sensor acquisition and the resulting pulse width modulation actuation. If an engineer attempts to compensate for this delay by increasing the proportional gain, or KP, the system becomes unstable because its heavy control actions are reacting to outdated sensor data. In setpoint control, tracking a moving reference means this calculation delay creates a permanent gap between the desired and actual position. The steady-state error, represented here by the formula ESS equals C over KP, remains strictly non-zero, forcing the joint position to constantly lag behind the command. Installing a faster processor does not solve this issue. A higher clock speed performs the math faster, but it does not eliminate the dead time gap between reading a sensor and outputting a physical voltage. As long as a control architecture reacts strictly to past errors, it is mathematically bound to suffer from high-speed phase lag. To eliminate this lag, the engineering approach must shift from reactive proportional integral error tracking to proactive feed-forward nonlinear control. Feed-forward architectures allow the drive system to utilize a complex dynamic model of the motor's behavior, generating control laws without requiring time-consuming computations to run strictly at the servo rate. An observer actively generates a future trajectory ahead of a moving target, calculating state prediction using a Jacobian matrix, GT. This calculation happens before the actual measurement update, entirely bypassing the reactive blind spots of discrete sampling. By accurately predicting the future state mathematically, the system effectively deletes the calculation delay from the physical control loop. Implementing predictive math requires a rigid hardware foundation. To eliminate timing jitter, high-frequency pulse width modulation duty cycles must be locked to ultra-precise hardware interrupts. The interrupt service routine must execute a precise sequence, read the encoder, calculate the new trajectory, and set the PWM output, all at a constant rate. This schematic details the hardware solution. The PWM2 output is wired directly into the timer input pin, synchronizing the servo calculation with the PWM subsystem. The timeline shows a 15.625 kHz PWM rate, explicitly synchronized to trigger the servo update interrupt exactly every 16 cycles. The motor responds to this setup by acting as a linear amplifier, physically time averaging a high-resolution pulse width modulation that updates every 62.5 nanoseconds. This hardware-locked synchronization translates a mathematically perfect predictive model into flawless, zero-latency physical movement. Hardware synchronization solves internal latency, but a perfectly synchronized loop will still fail if the load inertia shifts abruptly during operation. To maintain stability at high speeds, the drive requires real-time auto-gain tuning. This flowchart illustrates the tuning algorithm monitoring the motor. It estimates mechanical resonance and shifting load inertia on the fly, instantly adjusting an adaptive filter node. This suppresses vibrations without interrupting the primary position and velocity control loop. Absolute stability at extreme speeds requires a system capable of dynamically measuring and adapting to its own changing physical mass in real time. Even with adaptive filtering, large step disturbances, like a tool head striking a solid object, can trigger a failure condition known as integral windup. When a massive following error occurs, the physical system output flatlines at its limit, but the mathematical integrator continues to endlessly accumulate error. When the system clears the disturbance, this bloated integrator violently unwinds, commanding overcorrections and massive mechanical oscillation. The architectural fix for this is strict intervention. The PID implementation must explicitly stop the action of the integrator the exact millisecond output saturation is detected. By cutting off the integrator during physical saturation, the architecture guarantees a smooth recovery from sudden impacts, preventing the machine from destroying itself. This benchmark isolates the tangible results. Under heavy loads, a standard PI-controlled DC motor yields a sluggish 7.2-second rise time and requires 9.3 seconds to settle. Applying the DC servo architecture drops rise time to 0.8 seconds, shrinks settling time to 6.0 seconds, with a controlled peak overshoot of 1.22. Despite driving the hardware at extreme speeds, the predictive architecture successfully limits physical oscillations to a moderate, safe level. These specific metrics, maximum computing speed, the absolute shortest sampling times, and extreme dynamic performance, are the definitive physical hallmarks of true servo control. The benchmark data proves that tightly synchronized predictive loop architectures possess a clear physical superiority over standard reactive loops. High-speed motion control relies on three pillars: proactive feed-forward state estimation, absolute hardware-level PWM synchronization, and continuous real-time auto-tuning. Combining these elements allows engineers to completely bypass the theoretical phase lag limits of traditional digital sampling. Precision in high-speed motion control arises from the integration of temporal synchronization and predictive system modeling, surpassing the limits of raw calculation speed.
Thanks for watching. Please visit the channel for such more content, and don't forget to subscribe the channel and like if it is helpful to your knowledge, and comment if something is wrong.